This is the GMAT 41 Support Student Education Initiative Program. You are welcome to our chemistry class. I want to use this opportunity to appeal to you friends to talk about these programs to your friends, inform them and encourage them to contact us so as to join this program in order for us to contribute and help them in a solid foundation in maths and science. In this video, we are going to look at the topic valency, formation of compounds and chemical formulae. A very wonderful topic as long as chemistry is concerned. At the end of this topic, you should be able to define valency of an element or a radical. It is also expected that you should be able to use the concept of valency to write chemical formulas correctly. You see, friends, the issue of writing chemical formulas correctly has been a greater challenge for students. And of course, without having a knowledge of how a chemical formula is written, then of course it becomes difficult for us to even balance a chemical equation. And once we cannot be able to do this, then when we are studying all these elements, compounds, it becomes quite difficult to understand what we are talking about, which is largely what chemistry is built on. Therefore, I appeal to you and urge you to give your attention to this topic. To start with, what is valency? Elements have what we call valency. Radicals also have what we call valency. So what is valency of an element or a compound? Simply put, it is a combining power of that element or radical. The combining power of that element or what? Radical. That is what valency is. When we talk about radicals, just like we have on the board here, radicals are simply a group of atoms of different elements which come together to form a single unit. So you could have seen something like this before in chemistry, possibly OH negative, NH4 positive, SO4 2 minus, CO3 2 minus, even NO3 minus, and many more. You notice that this, well, I refer to them as substances. Alright, they are ions, right? They are made up of atoms of different elements. For example, in this hydroxide ion, you have oxygen and you have what? Hydrogen, which are atoms of different what? Elements. But they come together to form a single unit with an ionic charge. That we refer to as what? Radicals. From what I've explained, we've been able to define valency, and we said it's simply the combining power of an element or a radical. We've also defined what radicals are, or what a radical is. Examples of radicals have also been mentioned as you have on the board. Valencies can either be positive or negative whole numbers. Please take note of that. Okay, I don't think I've said or remember saying where valency happens to be a fraction. They are always whole numbers, either positive or what? Negative. Generally, when dealing with elements, we talk about metals, we talk about non-metals. These are the two general classifications of our elements before we now start going deep into, talking about the metalloid, talking about the transition elements, the actinide, the lanthanide. Just like we're going to study subsequently as we're moving on in this subject under periodic table. But before talking about all this lanthanide, actinide, metalloid, it is important for us to know that generally elements are classified into metals and non-metals. Now, the valency of metals are generally positive. Don't forget that. On the board here, I've chosen to write that using blue marker because it's an important point for you to take note of. Metals have positive valencies, and this is because during chemical reaction or combination of metals, they give out electrons. Electrons are negatively charged. Every atom has what we call electrons and protons. Protons are positively charged. Now, if an atom during chemical combination or reaction gives out electrons, which is what happens in the case of metals. When they give out electrons, then the protons, which are positively charged, will now become more than the electrons. So you see, metals, when they react, will have more positive charges than negative charges. Therefore, their valency is usually positive. And that leads to what we call cations. Cations. So take note of that. The valency of metals are positive. Like I said, it's because during reaction they lose electrons. So they will have more protons, which are the positive charges of an atom. What about non-metals? The valency of non-metals is negative. And this is because during chemical reaction, non-metals, they receive electrons, which means the number of electrons that non-metals will possess during chemical reaction will be more than the number of protons they have. And whereby the number of electrons become more than the number of protons, it means that that's a ion. Because in that case, after they've reacted, we refer to them as ions. Are you following? It will have more electrons, which are negative charges, compared to the protons, which are positive. So since non-metals react to gain electrons, excess electrons give them that negative charge. That is why the valency of non-metals is negative. We have that here written on the board. Why is it very important for us to take the study of valency chemistry seriously? Like I said from the outset of this topic, the study of valency is very, very important. In fact, we cannot overemphasize it. There are a lot of things in chemistry that depend on the knowledge of valency. As a matter of fact, some of the challenges that we may have had in the study of chemistry are linked to valency. Just like I said earlier, imagine someone talking about calcium trioxocarbonate 4, but you don't know the chemical formulae of this compound. Just imagine someone studying hydrogen chloride, but then the person does not know the chemical formulae of hydrogen chloride. That is definitely going to be a very big challenge, is that not so? Now when you move on into balancing of chemical equations, compounds are formed, compounds are broken during balancing of chemical reaction, just like when we write it on paper. If we don't know the chemical formulae of a particular compound that is going to be formed, it's going to be terrible to be able to withstand such study. Have you asked yourself this question? Why is it that water is always written as H2O? Why can water not be written as H2O2? H2O2 will be told that it is hydrogen peroxide. Why? Why is hydrogen chloride written as HCl? Why is it that hydrogen chloride is not written as H2Cl? These are serious questions we want to give attention to. To understand this, why a compound is written in a particular form, we need the absolute knowledge of valency of elements and radicals. How do we determine the valency of metals and the valency of non-metals? That's the next thing I would like us to know. And here on the board, I have this. Let us assume that I choose N to be the valence electron of an atom. Please take note, I pronounced valence electron. I did not say valency. Please, there is difference between valency, that ends with CY, and valence. Valence is CE. You can see that on the board. Valence electron is simply the number of electrons in the outermost shell of an atom. That is what valence electron is. For example, sodium atom has 1 electron in its outermost shell. So the valence electron in sodium is 1. Oxygen has 6 electrons in its outermost shell. So the valence electron of oxygen is 6. But it's not the same always as their valency. So how do we get the valency of metals? And how do we get the valency of non-metals? So we'll have this on the board I've put up for you. For metals, if we assume that N should be the valence electron, that is the number of electrons in the outermost shell of an atom, then for metals, valency of metals will simply be equal to N plus. That is the number of electrons in the outermost shell, then plus. Does that make sense? That's why the valency of sodium, as you're going to see subsequently in this topic, is simply 1 plus. Is that okay? Valency of aluminium is 3 plus. Valency of magnesium is 2 plus. So it is simply the number of electrons in the outermost shell, you put plus there. That's for metals. What about for non-metals? You can see a very simple relationship I've given you now. For non-metals, the valency is equal to the number of electrons in the outermost shell of that non-metal minus 8. So valency of non-metals is simply valence electron minus 8. And that will always give you a negative valency. Take for instance, chlorine. The number of electrons in the outermost shell of chlorine is 7. So the valency of chlorine is going to be 7 minus 8, which will give you minus 1, right? What about oxygen? The valence electrons of oxygen is 6. That's the number of electrons in its outermost shell. So we can say for oxygen, N is equal to 6. So how do we get the valency of oxygen? It's simply that 6 minus 8. You know, 8 is the maximum number of electrons. We say, okay, from L shell, LMN shell upward, you know, they carry maximum of 8 at this level of study. Are you following? So we have to subtract that total number of electrons that a shell is meant to carry from the valence electron. That's what we do for non-metal. So in the case of oxygen, you're going to have 6 minus 8, which is equal to minus 2. No wonder if you see oxygen in most cases to usually be written something like this. Maybe O2 minus. Have you seen that before? Good. So that's how we obtain the valency of metals and non-metals. Next, I would like us to talk about the first 20 elements. Because when we know about the first 20 elements, possibly their atomic structures, which will help us determine the electronic configuration, the number of electrons in each shell, then we can easily get the valency of each atom. And then we will start doing a lot of things with this knowledge. We are going to give attention to the first 20 elements, and then we would look at their electronic configuration, and of course from the last number in the electronic configuration we can actually determine the valency of at least the first 20 elements. So on the board here, we have this chart we are going to use. Okay, so we've got this table. We're going to go through the table and see what we have there. In the table, we have 3 columns, is that not so? You can see that. One of the columns is a column for elements. The other is a column for electronic configuration. The other is a column of valency. All of these, we are going to actually deal with them. We're going to study them, make use of them in the course of these subjects. So, are you ready? Good. I want to state, please, that you want to make sure you know the first 20 elements. Have them at heart. You have to say them without really thinking about them. Yeah, very important when you're talking about studying chemistry. Now, the first element is hydrogen. I've tried to write the atomic numbers as well as the relative atomic mass of these elements. I hope you're following, right? Now, the way these elements are arranged here, please make sure you don't misplace them. Don't scatter them, please. This is how the first 20 elements are arranged. It follows the serial number. Hydrogen is number 1, helium number 2, lithium number 3, beryllium number 4, boron number 5, carbon number 6. You move on down to calcium number 20. Alright, now the number that is written down here is the atomic number. It's also the same as the serial number of the atom. You have to jot this down. I want to believe you have your notes with you. So as you're listening to this lesson, you have to jot down important points. Okay? Now, the number written down here is the atomic number. It is also the same as the serial number, that is the arrangement of the element. It is also the same as the number of electrons and the number of protons that an atom would have when the atom has not reacted. That is when the atom is electrically neutral. Because the number of electrons and protons for an electrically neutral atom, they are the same. Now the number written on top here, we refer to it as the relative atomic mass of that element. RAM. Relative atomic mass. When we treat isotopes and isotopy, you will learn how we calculate and obtain that value from the basis of carbon-12. So let's quickly look at what we have here. So the first is hydrogen. The electronic configuration of hydrogen is 1. Hydrogen has only 1 shell. Okay, talking about basic chemistry. So looking at the electronic configuration, it has 1 shell and 1 electron. So you can see that the valency of hydrogen is mostly +1. But sometimes also you can see it as -1. In the case where it is -1, then it means that that hydrogen is actually maybe reacting with a metal, so that hydrogen will withdraw 1 electron from that metal. And the shell of hydrogen, which is only 1, the K shell, the first shell, remember, if you're using the circular notation to write atomic structure, we have the K, L, N, N, O, P, Q shells. K shell can contain a maximum of 2 electrons. It doesn't contain more than that. That's the first shell of an atom, 2 electrons. Then from L, N, N, and then onward, they contain maximum of 8, which is why we talk about octets. That one which contains maximum of 2, we refer to it as duplet. Please, dear student, as you're listening to these points, make sure you jot them down in your notes. Very important. Is that okay? Those are going to form your jotter. Alright, per se. It's true you're going to copy this into your notes, but these points you're making, make sure you pen them down below this table you are going to draw in your book. Alright, so because the first shell can carry a maximum of 2 electrons, anytime you have hydrogen reacting with metals, then you see the valency as 1 minus 2. That is 1 minus the maximum number of electrons it can contain, where 1 is the number of electrons in its outermost shell, which is shown by this electronic configuration 1 here. If you do that, 1 minus 2, you get minus 1. However, in most cases, how we see hydrogen exist when talking about its valency is plus 1. Is that okay? Now I'm going to speed up a little. We go on to helium, atomic number 2. The electronic configuration of helium is 2 because it has only one shell still, which is the K shell. And that K shell is completely filled. Like I said, K shell can take maximum of 2 electrons. That is why in periodic table, you will see helium in group 8 or 0, or group 18. If you start moving on into higher chemistry, we talk about the 18 groups. But no, let me not take you there. We'll be talking about the 8 groups with 4 periods, because I am limiting these studies at this level to the first 20 elements. Is that okay? So, helium has a completely filled outermost shell. In fact, helium is the only atom that attains the duplex structure. Take note of that as well. Now, how do we get a valency? Helium has no valency. Of course, that's the reason why it does not react. Remember group 8 or group 0 elements. Helium, neon, argon. If you continue down, you have things like xenon, krypton. Alright? They do not react because their outermost shell are already completely filled. So no space for any electron to enter again. That is why in this case, to talk about the valency, like I said, we don't discuss the valency of group 8 or group 0 element. As a proof, you could see this. The valence electron, that is the number of electrons in the outermost shell, minus the maximum number of electrons it can take, which is 2, you know. So you have 2 minus that 2 maximum electron it can take. So you have 0. And that's why we said there is no need of talking about the valency. So it doesn't have any valency. It just says 0. Alright, we move on. Lithium. Lithium, you can see atomic number 3, but look at the relative atomic mass is 7, okay? When problems are given to you in questions, most times, okay, in exams or your school tests and the rest, okay, normally the relative atomic mass of the element are usually given. Alright, so why as a scientist to be a chemistry student, it's important for you as much as you can to memorize the relative atomic mass of these elements. Alright? If you can memorize them, fine. However, most cases when questions are given to you, the relative atomic mass is usually given in the question. Alright, the electronic configuration of lithium is 2, 1. The first shell, which is K shell, will carry 2 electrons, is complete. So you need to add another shell, making it the second shell, the L shell. That will now carry only 1 electron, because lithium is atomic number 3, it has 3 electrons and 3 protons. And this electronic configuration is simply the number of electrons in each shell of an atom. So it's going to be 2, 1. Now, this is a metal. How do we usually identify metals for the first 20 elements? Any atom that the valence electron, that is the number of electrons in the outermost shell, is less than 4. It's less than what? 4. So talking about 3, 2, 1. Those elements are referred to as metal. So you look at this, the last number here in the electronic configuration are the valence electrons. They are the number of electrons in the outermost shell. So once that number is less than 4, then you know that that atom is a metal for the first 20 elements. Is that okay? Alright, so lithium here, the valence electron is 1. So the valence will be plus 1. Remember I told you for metals it's simply N plus. Just put plus in the valence electron, that's all. Alright, we go to beryllium, the same thing, plus 2. Boron, the same thing, plus 3. When you now go to carbon, carbon shows 2 different valency. One of them is plus 2. The other is plus 4. That is why you could hear something like carbon 4 oxide, carbon 2 oxide, which is the same as carbon dioxide and carbon monoxide. Is that okay? Alright, let's move on. Nitrogen, the valence electron is 5. Nitrogen also shows 2 valencies. One of them directly by doing 5 minus 8. If you take note of this, the number of electrons in the outermost shell now is 5. It's greater than 3. Is that also greater than 4? It's greater than 4. That 4 serves as a limit. That is group 4 element where carbon is. Divide the periodic table into metals and non-metals. So above 4, they are non-metals. And to get a valency is simply the number of electrons in its outermost shell, which is valence electron minus 8. So look at that here. That will give you minus 3. However, take note that nitrogen also have minus 5 valency. Please take note of that. Okay, we'll move on to oxygen. You say that valence electron is 6, so the valency will be 6 minus 8. Where 8 is the maximum number of electrons that the outermost shell of oxygen is supposed to contain. So it's going to be the number of electrons in its outermost shell, which is 6 minus 8. So you get minus 2 there. For fluorine, if you work it out, you get minus 1. Go to neon and see. Neon is in group 8. You can see the outermost shell is complete. 8. The second shell, the L shell. If you do 8 minus 8, you get 0. So simply, we don't talk about the valency of that group 8 or group 0 element. I've said that before when I explained that of helium. Let's move on to sodium. From sodium, you see the second shell is complete now with neon. So moving to number 11, you need an extra shell, making it 3 shells. This one in K shell, this one in L shell, this one in N shell, the third shell. So if you look at this, the valence electron in the electronic configuration for sodium is 1. It is less than 4, is that not so? Therefore, sodium is a metal. So the valency will be plus 1. Same with magnesium, the valence will be plus 2. You can see each valence electron here. Aluminium, the valence electron from the electronic configuration is 3, so the valency will be plus 3. Go to silicon, is plus 4. When you move on to phosphorus now, phosphorus, the valence electron is 5. So it's a metal, you're going to do 5 minus 8 to get minus 3. And once again, phosphorus still shows another valency, which is minus 5. So take note. Sulfur, its valence electron is 6, so you do 6 minus 8, you get minus 2. Sulfur happens to show up to 3 valencies, alright? One of them is minus 2, the other is minus 4, the other is what? Minus 6. That is why you could hear something like sulfur 4 oxide. We also have sulfur 2 oxide. We're going to meet all these things as we move on in this course. SO2 is sulfur 4 oxide. SO is sulfur 2 oxide. SO3, there is this gas we use in the contact process during the preparation of tetraoxosulfate 6 acid. That SO3 is sulfur 6 oxide. So you see that sulfur shows up to 3 valencies, oxidation states. Okay, now we move on to chlorine. Valence electron there is 7, so 7 minus 8, you have minus 1 as the valency of chlorine. That takes us to argon. Argon is a noble gas, a rare gas in group 8 or 0. Of course, you know what that's going to be already, but that's 0. The third shell is now complete with argon. So you move on to the N shell. You need to now add an extra shell in order to talk about potassium. Alright, that extra shell is in 288. The last shell of potassium, its valence electron is 1. Potassium is atomic number 19. If you add this thing up, you will get that 19. So, it's a metal. The last electron you can see is less than 4. So, its valence is simply plus that number, which is plus 1. Same with calcium, plus 2. So, you can see this. We've learned a lot of things from this chart we have in this table. So, you draw the table in your book, and then look into it, think about all the things we've said. Replay this video again, and make sure you grab a better idea and knowledge from this. There are lots of things that chemistry is based on, which I've explained just from this table. It is now time we are now going to learn how compounds are formed. First, binary compounds. For example, if you have sodium and chlorine, they react to give you sodium chloride, and you write the chemical formula as NaCl. What about calcium chloride? Reaction between calcium and chlorine. Hey, the compound is written as CaCl2. Where did that 2 come from? So, having known the concept of valency, it's now time. We're now going to move on to understand how compounds are formed. Is that okay? And then, this will move us into writing the correct formulae for a given compound.